Okay, the last little podcast for Unit 3, Area Study 2. This one's on immunity, and I should be able to get through it in 15 minutes, I hope. But you know me, it's not always the case. But there's only 4 really key areas this one, so let's get into it. We've talked about, in the last podcast, about memory cells. So if one has natural immunity from a disease, one is it's natural and it's active immunity. We have been given the disease. In this case, we've come across the picture there is of varicella, of chickenpox, and we've come in contact with it. People come in contact with it all the time. It's a very common human disease, and we quite quickly get sick, but we quite quickly produce memory cells, and those memory cells remain in our system. So while I've had chickenpox as a child, and it was quite nasty, I've never had chickenpox again in that sense, but I've probably been infected over and over again. But every time my memory cells kick in, and I never actually get to see those sort of pox across my body. So this is natural immunity gained by exposure to a pathogen, creating memory cells. It's also what we call actively acquired. But we can also have an artificial immunity. So it's active still, but instead of getting chickenpox, I can give you a vaccination for chickenpox. And it's just as effective because, again, it gives you the antigen that you would normally expect to find on a chickenpox virus, and your body makes memory cells. And therefore, if you are to come across chickenpox, then you would have memory cells ready to respond, and you would respond quite quickly and effectively and deal with that disease. So we call that still actively acquired, but an artificial active acquiring. We make vaccines in 2 ways. We talk about attenuated vaccine. So attenuation takes out that agent which causes the pathogen to be infectious, making it reasonably harmless, certainly less virulent. It's not going to make it very, very sick, but retains the antigens, so your body learns to make it without becoming ill. Or we can actually kill the pathogen, so it's an inactivated vaccine. We've killed the pathogen, but again, we've maintained the important antigens so you can make memory cells. And in the outcomes, they're the same in both cases. You will now have memory cells for that particular disease. So immunity is a really useful thing because it protects us against stuff that otherwise makes us very sick very quickly. We can passively acquire immunity. Now, this is not a great deal of use long term, but in the short term, like a developing child, it's very, very useful. So the classic is during pregnancy, the mother's immune system essentially protects the child. So it's the mother's antibodies that are protecting it. Not all her antibodies will cross the placenta, but most do. And the baby has protection from a wide range of disease while still in utero. Having given birth, the baby will receive a lot of those antigens still, not all of them, but most of them, across the milk. So milk, breastfeeding is one of those really important things to do in the early years of your child. Months, especially fairly 6 months, if not a couple of years, while a child's own immune system becomes strong enough to deal with its environment. But in both cases, once you're born and you stop breastfeeding, you don't have memory cells. You haven't met the disease. You've been protected by somebody else's memory cells. You have no memory of it. And you need to start creating your own. We can obviously also give you somebody else's antibodies. So if you're very, very sick, and I've had the disease before, we could actually extract antibodies from my memory cells and antibodies from my bloodstream and inject them into your bloodstream and give you some protection while your body catches up. But again, it's short term. And we talk about vaccination and the idea of herd immunity. So when we vaccinate a population, they normally try to get between 92 and 95% of the population completely vaccinated. So if we see this here, these blue people are not immunized, but still healthy. The red ones are not immunized and sick and contagious. and the other ones, in this case, have been immunised and are healthy. So in this population here, 2 people arrive carrying this disease. Nobody's immunised, and so most people get sick. In the bottom one, most of our people here have been immunised. A few haven't, but the vast majority have. Our 2 sick people arrive, and the ability to pass that disease to the unimmunised is really quite difficult because the herd protects them. So we call that herd immunity, or herd immunity. And it's why health officials push for a really high uptake of vaccination. So we know that we can protect people from really life-threatening diseases. And the whole debate around whether or not we should vaccinate is just a no-brainer from a scientific point of view. Any family that's had a child with polio, I had the great misfortune when I was 8 years old to have chickenpox, mumps and measles in the one winter, and it undermined my immune system. It still does undermine my immune system. Huge impacts. Those are things you've all been vaccinated for. You know, next generation, couple of generations down the track, and you've been vaccinated for them. These are diseases which cause massive costs to our hospital system, death in families, debilitating diseases which may leave you permanently disabled. We don't need to have people sick with these diseases. We can control them. And we're not making you sicker. You know, other problems don't exist. There are also a couple other things we need to think about with our immune system. And one of those is the idea of an autoimmune disease. And there are a number of them. The ones we hear most about are things like pernicious anemia, so lack of iron in your blood for carrying oxygen. Multiple sclerosis, a major one that we've spent a lot of time and effort trying to do something about. Rheumatoid arthritis, type 1 diabetes, in one of its forms, are all seen as autoimmune because the cells belong to your body, but your immune system fails to recognize them and in fact treats them as antigens presenting as non-self pathogens. So your immune system starts to kill them. In the case of multiple sclerosis, the oligodendrocytes, that's hard to say, oligodendrocytes, which create myelin sheath, are actually destroyed. So this diagram here is showing the scarring in the myelin sheath, and that disrupts the ability of the nervous system to send messages. And as a person with MS develops, their transmission of nerve messages becomes problematic, and in time death will occur. We've spent a lot of time trying to solve that one. Still a long way from working out what the hell's going on. We also have things called immune deficiency diseases, and the obvious example of that is AIDS. So the human immune virus creates a condition known as acquired immune deficiency. It's quite an invidious little fella because the HIV virus actually hides within helper T cells, which are those T cells which look for virus-invaded cells. So it sort of re-undermines our immune system. So what you end up with is a depleted immune system. And no one who dies with AIDS dies of AIDS. They will die of gastro, common cold, chickenpox, the flu, things that don't normally kill people, especially not in the Western world. But because their immune system's been depleted, the ability to protect themselves from other diseases is greatly undermined. Well on the way towards cures and treatments. Certainly treatments are in the Western world are keeping people alive, and cures aren't too far away. There's a number of major advances being made. Human trials are yet to start, but there's some big leaps being made. And then of course there's people like myself who have allergic reactions, and many of you here in the class probably do too. And it's actually a hypersensitivity because the non-self presenting antigen will cause no damage. So what our immune system is responding to is not something which will make you ill. So in my case it's the pollen from conifers and grasses, particularly ryegrasses. So for that sort of September through to early December I'm in trouble. And I produce a huge amount of mucus, and I feel tired and irritated, I feel swollen. All that huge inflammation process occurs. So what's going on? In most cases, the immunoglobulin E, also IgE, are produced in reaction to the presence of the antigen. And we'll find them often called allergens in this case. The antibody-allergen complex then attaches itself to mast cells, causing them to lyse and release great piles of histamine, cytokines, and all the inflammatory molecules. This causes the immune system to rush to the area with lots more blood tissue and swelling and inflaming and heating up the space, so you feel hot and tired. And the histamines cause smooth muscle to tighten, so in many people, of course, this can be a real problem with breathing, especially if they're asthmatic, because it undermines the airways. And you just have to put up with it for quite a while. So, of course, we take antihistamines to try and counteract the effect of the histamines. So your body's full of chemicals fighting each other, and you get pretty worn down. Unless you get anaphylactic shock in response, which again is a hypersensitivity, it is just a source of irritation. It's just one of those things you learn to live with and deal with and have your drugs for. Some people have used desensitizing treatments, which work quite well. But essentially it's just one of those things that many of us put up with in many ways. What's it called? The bowel disease, which Crohn's is a allergic reaction. It's a hypersensitivity. A number of diseases fall in that situation. Can't do much about it. The other one, of course, is the idea of cancer. And cancerous cells, of course, don't lack antigens, but they're self-antigens. They belong. They're your cells. And one of the interesting new treatments that the course would like you to know about is this idea of a monoclonal antibody. So that we culture the B cells in the lab and get them to produce lots of antibodies. Those B cells are cloned with plasma cells, so from tumours, creating what's known as a hybridoma. And the hybridoma is able to divide and clone itself repeatedly because there's no apoptosis. Right? It's a cancerous cell, so you get lots of clones. And then the antibodies produced from that technique can actually be designed to target specific cells and treat diseases, including cancer. The cloned antibodies can be used as a drug to either trigger the immune system attack, so that we're now highlighting these cells as a problem, so the immune system attacks them. Can block signals so that replication stops, or can be used to actually transport toxic or radioactive materials to the marked cell. So they're really quite an interesting way of going about treating cancers, and there's a huge development in these monoclonal techniques. But it's an interesting adaptation of our knowledge of the immune system and of cell replication. And that is your lot. So that's area of study 2 for Unit 3 in 5 rapid podcasts.